Trigonometry, Chapter 6, Inverse Circular Functions and Trig Equations, Section 1, Inverse Circular Functions, Video 3, Domain and Range of the Other Inverse Trig Functions. This series is based on content from Pearson's Trigonometry 12th edition by Lial, Hornsby, Schneider, and Daniels. In the previous video, well, 2 videos ago, we determined the domain and range of f of x equals sine inverse of x by analyzing the graph of f of x equals sine of x and adjusting the domain so the graph would satisfy the horizontal line test. The domain of f of x equals sine inverse of x is -1 to 1 inclusive, and the range is negative pi over 2 to pi over 2, again, inclusive, meaning including the endpoints. In this video, we determine the domains and ranges for the remaining trig functions. This will be done similarly to how it was done in the previous video, but at a brisker pace. Let's start with cosine inverse of x. Now below is the graph of f of x equals cosine of x. As with the graph of f of x equals sine of x, the graph of f of x equals cosine of x miserably fails the horizontal line test. Any horizontal line that intersects it will intersect it an infinite number of times. We fix that by taking a smaller piece of the graph. If we restrict, I meant to ask you what it was going to be, and it just got exposed, whatever. If we restrict the domain to 0 to pi, we keep all values associated with quadrant 1 angles, which is 0 to pi over 2, and keep the largest part of the graph possible that still satisfies the horizontal line test. If we had gone to the left of this, then we would have violated the horizontal line test on this hill here. Thus, f of x equals cosine of x, the one in green, with domains 0 to pi, left to right, and range -1 to 1, bottom to top, has inverse function. Before we describe it, notice that the green graph is reflected across the red line to get the purple graph, and each of the corresponding endpoints coordinates were reversed. 0, 1 became 1, 0. Pi comma -1 became -1 comma pi. So the inverse function is, in purple, f inverse of x equals cosine inverse of x with domain -1 to 1, left to right on the purple graph, and range 0 to pi, bottom to top on the purple graph. For f of x equals tangent, we achieve the same result by restricting the domain to between the two asymptotes bounding the center branch. Here's the entire graph of tangent, or at least the part that I'm showing you, separated by its vertical asymptotes at odd multiples of pi over 2. I highlighted the one in the middle in green. That's the one we're going to keep. We only need one branch. More than one branch, we violate the horizontal line test. And by keeping just the middle branch, we get the biggest part of the graph that contains quadrant 1 values, which is 0 to pi over 2, and does not violate the horizontal line test. So here's the results if we reflect it. First, let's go back over here for a second. When we keep this, we are only keeping the part between negative pi over 2 and pi over 2, not inclusive because of the asymptotes, but the range is from -infinity to infinity, all the way down to all the way up, which is what's summarized on the left here. But when we reflect it across the diagonal line, this branch goes sideways, and the vertical asymptotes become horizontal asymptotes at pi over 2 and negative pi over 2. I mentioned in my algebra class when we were doing rational functions that a rational function cannot have two different horizontal asymptotes, but there are some functions that can. This is one of them. F inverse of x equals tangent inverse of x does have a domain from -infinity to infinity, but the range is capped between negative pi over 2 to pi over 2, exclusive because of the asymptotes. Now, a similar approach can be used to find the domains and ranges of the other inverse trig functions, but we're just going to summarize them. Here are the graphs, domains, and ranges. There's a lot on this next slide. This is courtesy of the textbook that I am using to base this series on. Here we have the graphs of inverse cotangent, inverse secant, and inverse cosecant. And notice that the inverse secant and cosecant ones are broken. If you go back and look at the original graphs of secant or cosecant and try to follow the same mantra that we did before, keep the quadrant 1 stuff, but also pick up the negatives we're going to have to jump across an asymptote. So for cotangent inverse or arc cotangent, the domain is negative infinity to infinity, and the range is 0 to pi. For inverse secant, the domain is, and they're not listing it here, which bothers me. The domain for inverse secant or arcsecant is from negative infinity to -1, and then it jumps from 1 to infinity. And then the range is between 0 and pi, except not pi over 2 because of this horizontal asymptote. And the same thing for cosecant. The range is from negative infinity to -1, and then the other part is from 1 to infinity. And the domain is between negative pi over 2 and pi over 2 inclusive, but excluding 0 because of the horizontal asymptote. It is worth mentioning that the inverse secant and inverse cosecant functions, these last two, are sometimes defined with different ranges. We use intervals that match those of the inverse cosine and inverse sine functions, respectively, except for the one missing point because of the asymptotes. I am by far more concerned about inverse sine, cosine, and tangent than I am with these. Of these three, the only one that really has much play in future classes, such as Calculus 2, is secant inverse. But by the time you get there, it's going to be a non-issue. And I think that's the end. Well, here's the summary. Of all the inverse trig functions, domain, and ranges, as we continue, we will focus on the quadrants represented by the range. I want to focus on this right now. When you're using inverse trig functions, the biggest issue students face is the range values, what is allowed to come out of an inverse trig function. Not necessarily what can go in it, but what can come out of it. The ranges represent quadrants. For example, sine inverse, the range is negative pi over 2 to pi over 2. But if you were to think about angles measured in standard position, negative pi over 2 goes down into quadrant 4, and then positive pi over 2 up into quadrant 1. So that's quadrants 1 and 4. Same thing for inverse cosine, whose range is from 0 to pi. So from 0 to pi sweeps through quadrants 1 and 2. It's almost more important, in my opinion, to understand the ranges in terms of quadrants instead of intervals, but they are what they are. Oh, so now you try and pause the video and try to answer the following. This is about what you see here. So if you didn't write any of it down, you might want to take a picture of it, pause the video, do a screenshot, however you take notes. Number one, which inverse trig functions have ranges from 0 to pi, inclusive or exclusive? Number two, which inverse trig functions have unrestricted domains? In other words, their domains include all real numbers. And number three, why is pi over 2 excluded from the range of secant inverse of x? Pause the video, give them a try. And again, if you need to, go back and get this. Here's your fair warning if you haven't answered them yet. Solutions in 3, 2, and 1. Cosine inverse and cotangent inverse have these ranges between 0 and pi. That's easy to see here. 0 to pi, 0 to pi. Which inverse trig functions have unrestricted domains? Again, pretty easy. That would be these two. As far as why is pi over 2 excluded from the range of secant inverse of x, well, it's because pi over 2 is excluded from the domain of secant inverse, of secant, excuse me. You might recall that secant is the reciprocal of cosine. Cosine of pi over 2 is 0. So the reciprocal of 0 is undefined, and therefore secant of pi over 2 is undefined. You can't put pi over 2 into secant, so you cannot get it out of secant inverse. Same thing with the other break here for cosecant.